Hello, I do welcome you to the revision of the Mpumalanga Province Grade 11 Physical Science Control Test written March 2024. So, if it is your first time to be on our channel, I kindly just ask you to subscribe and also turn on the notification bell so that if we post anything, you'll also be notified. Without much further ado, I'm going straight into the questions there. I will skip the instructions for the sake of time, but I do advise when you are in the exam to go through them to understand them. So I will start at question number one, multiple choice questions. The 1.1 is saying two forces F1 and F2 act simultaneously at a point in the direction as shown below. Which one of the following represents the resultant of the two forces? So here is the easier way. You just combine them to form a rectangle, right? So there we are. There we are. There is our rectangle. So if it is to be drawn, it has to come out like this, right? So, or it's more or less a parallelogram. So then what do? You simply co-join or join the diagonal. So that this diagonal here becomes a resultant force, right, with the direction that it is showing. So the resultant becomes that. So we are just checking which among our diagrams represents that. So we see that it is B. It is the one that resembles the one that I've just brought in there. So it becomes the easier way of bringing out the resultant of the two forces. So 1.1 is B. Let's go to 1.2. Vector S and vector negative S are acting at a point P. So the angle between the two vectors is, right. So if vector S is acting in this direction, it means vector negative x s is acting in the opposite direction if this is our P, right? Assuming we're just making it. So it means that the two are acting in exact opposite directions. So the angle that lies between them is 180 degrees. They form a straight line. So they are acting in opposite directions. So 1.2 is C. Right, let's go to 1.3. Right, 1.3 is saying the force that opposes the motion of a moving object relative to a surface is called, right? That's kinetic energy apparently for a moving object, and of course for a stationary object it becomes a static friction. Now, a static friction. So that's 1.3. Then it becomes B. 1.4. The measure of inertia is the mass of an object. It's important to also note that the mass is the measure of inertia. Right? The mass of an object is the measure of inertia. Just out of interest, it might interest us to know that inertia is the resistance of a body to a change in its state of rest or uniform motion in a straight line. Right? That's in inertia. Let's go to 1.5. A bucket is at rest on a table. Which one of the following is the reaction force to the weight of the bucket as described by Newton's third law of motion? Right. So our answer would be easier to identify if we can know what weight is relating. We know that weight is a gravitational force, and gravitational force is the force that the earth is exerting on an object. So in our case, it is the earth exerting a force on the bucket. So what shall be the reactionary force to the force that the earth is exerting on the bucket? Obviously, it's going to be the force of the bucket on the earth. So it becomes 1.5b as in relating to Newton's third law, because mind you, these are supposed to be two objects. When object A exerts a force on object B shall simultaneously exert a force on object A, equal in magnitude but opposite in direction. So it means the force that will be opposite, equal in magnitude but opposite in direction to the weight of the bucket shall be the force of the bucket on Earth. It's very important to note that. Right, so 1.5 there becomes B. Right, let's go to 1.6. 1.6 is saying, okay, two masses mx and my are placed at a distance r apart. A third mass mz experiences a zero resultant horizontal force when it is placed 3/4 from mx on the line between mx and my. The ratio of the two masses, mx and my, is. So our answer will be aligned from, we can get it from understanding that, of course, if this is 3/4 r and the whole distance is r, automatically is telling us that this remaining is a quarter r. Therefore, it means the ratio between the distances between mx and mz, and also mz and my, the ratio of the distance shall be 3:1. We are talking of the ratio of the distances is 3:1, right? Then with that now, if these are the distances, remember we deal with the square of the distance according to the electrostatic force Fe is equal to kq1 q2 over r squared. So according to the Newton's universal law of gravitation, we are saying F is equals to g m1 m2 over r squared. So we want the square of the distance. Therefore, if we square 3:1, it's going to give us 9:1, which apparently becomes the ratio of them two masses, mx and my. Where are we deriving it from? We are taking it from the ratio of the distances between the two, right? So basically we are saying the ratio of the distance, if it is 3:1, therefore we expect the ratio of the masses to become around 9:1. Why? Because the masses are varying with the square of the distance and not the distance itself. So our answer there is C, 1.6. It's C, right? 1.7, two charged spheres V and W are located on a straight line X, Y, and Z. Three points on the same straight line. The positions of X, Y, and Z are indicated in the direction of the net electric field at points X, Y, and Z is shown in the diagram below. Right? Which one of the following combinations represent the charges on each of the spheres V and W? Right. If we look at X, the direction it has taken is quite closer to V. Therefore, it means the net electric field at that point X will be much dominated by V. So it means the direction of V is the one which is causing. But remember, every point charge is a positive 1 coulomb charge. So it means what has caused this to happen is because V is repelling or is causing X to repel away from it. So what could be V? It's positive. Same applies if we look at Z. Z is showing us that since it is closer to W, it means the most dominating electric field is that of W. So we are saying, considering the fact again that Enet is acting to the right, knowing that there is a positive 1 coulomb charge at the point Z. So it means that W also carries a positive charge because it caused Z to repel away from it. So hence, from that token, we can easily again bring out the charges of V and W. They are positive. So we are saying 1.7 is A there, right? We are just using our understanding of the electric field at a point, how it works. Okay, let's go to 1.8. 1.8 is saying two charged spheres A and B carrying charges Q and 2Q respectively are placed on insulating stands as shown in the diagram below. Sphere A exerts force F on sphere B. What is the magnitude of the force exerted by sphere B on sphere A? Right, it might just interest us. Okay, the first things first, these two exert a force. If A exerts a force of F on B, apparently B is also exerting a force of F also on A. So our answer here is C, because they must exert a force of equal magnitude, though in different directions, but it's of equal magnitude. It might interest us again to say, why are these two charged spheres placed on wooden stands, on insulating stands, so as to avoid the charge to leak to the ground? Okay, let's go to 1.9 there. So we are answering 1.8 is C. I was just digressing to explain something else totally different. Don't mind. 1.9, the diagram below shows 2 points. 2 point charges Q1, 5 coulomb, positive 5 coulomb, Q2, negative 4 coulomb at a distance X from P. Right. So the net electric field at point P in terms of E is given by. Right. We might want to trace our steps to say, okay, how in the first place do we calculate the electric field? E net, of course, in our case, it is supposed to be equal to EQ1 plus EQ2, but do considering that these are vectors. Okay, so retracing our steps to say how are we calculating EQ1? EQ1 obviously is equal to, since E is equal to KQ over R squared, so it means EQ1 shall be equal to K multiplied by 5Q over X squared, right? That's the distance we have there, right? Then what is the direction? At P, there is a positive 1 coulomb charge. So it means P will be repelled away from Q1. So it will act to the right. So EQ1 is acting to the right. What am I trying to do? I'm trying to retrace how in the first place can we calculate the value or the magnitude of that net electric field. Okay, so that marks our EQ1. Let's go to EQ2. So EQ2 is again equal to K multiplied by 4Q over X squared. Now, considering that this is negative and this is positive, it therefore means P will be attracted towards Q2. So it means EQ2 is acting to the what? To the right. That's its direction. Meaning to say, when we are now calculating E net shall be equal to EQ1 plus EQ2, which is K 5Q over X squared plus K 4Q over X squared. These are like variables, they can be added. And when we add them, they're going to give us, we are going to end up having 9KQ over X squared, right? 5 plus 4 there. So we get 9KQ over X squared. But KQ over X squared, apparently that's E there, because E is equal to KQ over X over R squared from the start, right? So it means, therefore, our net electric field shall be 9E to the right. Apparently, it will be because both of these two were right. So since it's coming out as positive, it means it's also acting to the right. So our answer there becomes D. So 1.9 we are saying is D. Let's quickly go to 1.10. Right. For 1.10, we are saying which one of the graphs below represents correct the relationship between the electric field at a point and a charged sphere? Right. So we were saying E is equal to KQ over R squared. What is the relationship between E and Q? They vary directly, which means when one increases, the other one is also increasing. So it means that for 1.10, our answer is B. That's a direct variation graph. This is a direct variation graph. So that's the relationship that the two are having. Right. So we can go to question number 2. So those are the questions for the multiple choice there. 3 forces S, T, and U of magnitudes 300, 800, and 250 respectively act on a point as shown below. The forces are not drawn to scale. Okay, define a vector. Okay, we just define a vector as a physical quantity that has both magnitude and direction. That's a vector by definition. Okay, let's go to 2.2.1. Calculate the horizontal component of S. So we just want the horizontal component of X. As a matter of fact, which one is it? From the tail of S towards the head, following the horizontal and then the vertical dimension. It means we are taking this direction here. This is the horizontal component that the question is asking. Apparently, the one that goes down now marks the vertical component Fy. We can call it Sx or Sy, but I'll refer to it as Fx there. So Fx, right, considering the angle that we have here for 20 degrees, I am saying you can also do this. This becomes the vertical component, and this becomes the horizontal component. So that's your fx as well, in as much as this is your fx. So there are two ways in it means that you can calculate, because our 20-degree angle is the angle to the vertical and not the angle to the horizontal. I'm going to clear here so that the angle 20 degrees becomes clearer to see. So we are saying that angle of 20 degrees that we are seeing there, it is the angle to the vertical. So when I am calculating now the horizontal component, I have to say S multiplied by sine theta, because it is the angle to the vertical. So my theta becomes 20, sine 20, right? So considering the size of S is 300, so we simply say 300 times sine 20. And punching that on the calculator is going to give us 102.606043, which to two decimal places is going to be 102.61 Newton, right? Alternatively, we could have determined this angle here from this other diagram that I'm indicating here, right? This one. We are saying we can determine this angle how? By simply saying 90 minus 20, and that will give us 70. So we have now the angle to the horizontal now. So when we use that, we say now fx is equal to s cos 70. We are supposed to arrive at the same answer, 300 multiplied by cos 70. We'll still get the same result, 102.61 Newton. There are many ways of killing a case, so it's very important to know both ways. Right, so that's our horizontal component of S there we have just calculated. Let's go to the next question. Right, our next question is saying determine the vertical component of T. So in this regard, we are now calculating the vertical component of T. Right, for the vertical component of T, we can relate with the diagram again. From the tail of T, moving first in the horizontal and then moving in the vertical is the option we want to take. Sometimes we can say moving first in the vertical and then moving in the horizontal. It means we have to find this angle here, which in the same way that we found the 70-degree angle, we can just say 90 minus 15, the 15-degree angle that we are having. Okay, so I will not use this way. I will use this way here. So we are saying to calculate Ty, we are going to calculate it. That's our vertical component there. We are going to say, okay, I just want to erase this part. Right, so we are going to say our Fy for T, our Fty, it is actually equal to T sine 15. Mind you, our angle to the horizontal there is 15 degrees. We are using the trig ratios when we are performing those calculations, because we have formed a right angle triangle. Therefore, we are just using it trigonometric ratios, right? So we are saying we have 800, right, multiplied by sine 15, and that will give us, punching our calculator, 207.0552361. So to two decimal places, right? That's our force there. Same applies with the one that I'm making. Okay, root up here. And when you do take that direction, it means your vertical component becomes this one. And this angle shall be 90 minus 15, which is in 75 degrees. Right, so you can also say Fy is equal to T cos 75, whereby you have taken the angle to the vertical now and no longer the angle to the horizontal. Right, so it means you can still say 800 multiplied by cos 75, you will still arrive at 207.60 Newton. There are many ways of killing a cat. Right, so let's go to the next question. 2.3. 2.3 is now saying determine the magnitude of the resultant of all the forces acting at origin. Right, so we want the magnitude of the resultant force. So I'm still going to use the same diagram there, right? Okay. Okay, I just want to indicate it. Okay, so we want the magnitude of the resultant force. How are we going to calculate it? Right, we are to consider all the forces that we are having. Right. I'll first choose a certain direction as positive, but we are dealing with vectors. So I'm choosing right as positive. It's a choice that I've made, right? Then I'm going to calculate the resultant of the horizontal components. So I'll call it x, Rx, which means I'm calculating the resultant of all the horizontal components, that we are having, of all the forces we have. So starting within the 800, of course, we have already, we did calculate, of course, the vertical component. Now, this is the horizontal component of T. So it is going to be given by what? By 800 multiply by cos 15 using the trig ratios. So that's our Tx there, or our Fx due to T, right? Then we happen to have the 250 Newton force, but do take note of the 250 Newton. The arrow is pointing towards this point. That's where the arrow is, right? So because of that, from the tail here to the head, if we are going in this direction, which means I am saying ux is acting to the right. Hence, because of that, it's not negative, it is positive. That's one other key important thing to note whenever you are dealing with vectors. So I am saying the horizontal component of u is acting to the right, just like the horizontal component of t. We trace it from the tail to the head. It means it's moving to the what? To the right. And we have chosen right as positive, therefore it was positive there. So it also follows that for u, it's also positive due to that. So we will say plus 250, right? Cos what? What is the angle here? We have been given the angle here is 40 degrees. So 250 cos 40 degrees, right? Um, then we also have the horizontal component of S. Apparently, we have already calculated it, but it's acting to the left, yet we chose right as positive. Remember, when we calculated it at 2.2.1 there, it was acting to the left. So we, we have to subtract now. So we will say minus. That's 300 sine what? Sine 20, but we have already calculated, we can just place it as the figure or the value that we have already gotten, right? So what do we get? That gives us 861.6457 Newton, avoiding to round off our figures too soon before the final answer. So I'm going to keep them a bit. Then we go to the vector sum, or the resultant of the vertical components. So that's our RY. So RY, we are now considering, I'm going to take upwards as positive. I will take up as positive. It's a choice that I'm making, but it will determine which forces are going to be positive and which ones are going to be negative. Considering T again, T is acting upward, because if when I end the horizontal component here, I am going up now. So it means Ty, we did calculate it, 800 sine 15. We did calculate, we can just place again the value that you already got, and you just use that. Right. This time around, what about the vertical component of u? The vertical component of u from the tail towards the head of u, uy, or the vertical component of u, is no longer acting upwards, rather it's acting downwards. So we will subtract, because I have taken upwards as positive. So I will subtract, hence it's giving me minus 250, 250, right? So that's minus 250 then, sine 40, right? Using the trig ratios again, we are saying this is the opposite and hypotenuse. So 250 sine 40 minus, again, considering the vertical component of S, it's acting downwards. So since it's acting downwards, we are saying minus 300, minus 300, right? cos 20 using that angle of 20 degrees there. We are saying this is the vertical component. It's going down, right? So cos 20. So 300 cos 20, and that gives us minus 235.549. What does this negative imply? It's simply telling us that since we chose upward as positive and it's coming, our answer is coming out negative, it means this is acting downwards. So the direction is down. However, the instruction only wanted us to calculate the magnitude. So we shall focus on the magnitude. It means, therefore, R is equal to the square root of Rx squared plus Ry squared. All right, so substituting the values that we got, we are saying 861.647 squared plus 235. So that's 235 there, comma, that's 235, comma 5494. 235, comma 5494 squared. And that will give us 893.2619, which is to two decimal places, is 893.26 Newton. This marks the magnitude of our resultant force. The instruction was saying calculate the magnitude. Yes, we simply calculate the magnitude and not the direction. We didn't calculate the direction. Right, so that's 2.3 there. Right, let's go to question number 3. A picture frame lifted upwards by two ropes hangs freely on two adjustable pulleys as shown below. T1 of magnitude 180 Newton makes an angle of 15 degrees to the vertical, while T2 of magnitude 320 Newton makes an angle of 55 degrees to the horizontal. Right. Define the term resultant vector. Resultant vector is a single vector having the same effect as all other vectors acting together. That's in 3.1. 3.2, draw a free body diagram of all forces acting on the picture frame. Right, so we shall indicate our picture frame with a dot and a dot for the free body diagram. So we just draw a dot. Then forces, all forces, whenever we are drawing a free body diagram, they must start at the dot and going towards their correct direction. Right. So I will start with T2 here. There is the direction that T2 is taking. That's T2 there. Then we also have the direction of T1. Right, there is T1 there. There is T1. Right. Starting at the dot, it's connected to the dot. That's max T1. We've labeled it. Then we also have the gravitational force, the force of gravity, Fg. There is gravitational force acting downward. That marks the free body diagrams tend to be guided always by the marks that have been indicated. 3 marks there, it means we are supposed to have 3 forces also acting. 3.3, what is the magnitude of the net force acting on the picture frame? Right, so we are being asked the magnitude of the net force acting. Apparently, it is 0. F net is equal to 0 as it is it hangs freely. So it means F net is equal to 0 Newton. Right. That's our force, our net force there. Right. The next question is saying 3.4.1. Calculate the weight of the picture frame. Right. Since F net is equal to 0, we can take that advantage to perform the calculation for the weight, whereby we are simply saying, right, I just want to clear off my screen there. We are saying F net is equal to 0. So considering the vertical components of the applied of the tensions that we have T1 and T2, this is T1y and this is T2y. Right, the two of them are the forces acting upwards. And apparently gravitational force is the force acting downwards. So in the horizontal, in the vertical plane or in the vertical dimension, it means if we simply add the forces acting upward. They must be equivalent to the gravitational force that is acting downwards. In other words, we are saying T1y plus T2y minus Fg. Remember, right, if we have taken upward as positive, it means gravitational force is equal to is becomes negative. So these are the forces that must be equivalent to zero in the vertical dimension, right? So hence we can perform calculations based on that. So we can say T1 is 180, right? This, according to the angle, since we have been given the angle to the vertical, T1y can be calculated as in T cos theta, where our theta is the angle to the vertical. So we can take that advantage and say 180 cos 15. Please kindly take note, if we were using the horizontal, the angle to the horizontal, which is this one, which becomes 75 degrees, because this whole angle is 90 degrees. It's when we were supposed to now say T1y is equal to a T sine theta. We will say sine theta when the angle theta is the angle to the horizontal. Apparently, it is the angle to the vertical right now. So we have to say, and it is the one we have opted to use. So we are saying 180 cos what? Cos 15, right? Plus, then for T2y, I'm opting now to use the angle to the horizontal that I've been given. So I can easily say T2y is equal to T sine theta. So it's going to be 320. So I'm saying plus 320 sine 55, because my 55 degrees or the 55 degrees that has been given is the angle to the horizontal. So it's possible to say T sine theta when I'm calculating the vertical component, right? So I'm saying it's equal to gravitational force having transposed the gravitational force to the other side, because it's negative, it becomes positive. So it's equal to Fg, right? So simplifying that, I get Fg being equal to Fg, the gravitational force, which is our weight, is equal to 435.9953029, which is 436 Newton, wanting to indicate it that way. So that's 436 Newton, rounding it off to two decimal places. Right, so that's our Fg there. All right, let's go to 3.4.2. Calculate the mass of the picture frame. So we can now take advantage of the gravitational force that we now have and say Fg is equal to m times g. Therefore, it means m is equal to Fg over g by dividing by g both sides, dividing by g both sides. It means m is equal to Fg over g, where g is the gravitational acceleration. So Fg, we have just calculated it, our weight, 436, divided by 9,8, and that gives us 44,492 decimal places kgs. That's the mass of our picture frame, right? Then let's go to the next question. The next question is now saying the pulley system is now adjusted uh, such that 55-degree angle is increased to 80 degrees, while the 15-degree angle is decreased to 5 degrees. Will the picture frame move upwards or downwards? Fully explain your answer. Right, the picture frame will move upwards. Here is our diagram. Right, it will move. It will go upwards because the vertical components of T1 and T2 will apparently increase. So due to that, the picture frame will move upwards. If we increase, the instruction was saying when the 55 is increased to 80 and when the 15 degrees is decreased to 5, it means that has an impact of increasing the vertical components of T1 and T2. And by so doing, it causes the picture frame to move upwards. Okay, let's go to the next question. The next question is saying the 8 kg block resting on a rough horizontal surface is connected by a light inextensible string passing over a light frictionless pulley to another block of mass 2 kg. The 2 kg block hangs vertically as shown in the diagram below. The force of 80 Newton is applied to the 8 kg block at an angle of 20 degrees to the horizontal, causing the block to accelerate to the right. The coefficient of kinetic friction between the block, between the 8 kg block and the surface of the table is 0.2. Ignore the effects of air friction. Number 4.1 states Newton's second law of motion in words. Right. It simply states that when a non-zero resultant force acts on an object, the object will accelerate in the direction of the net force at an acceleration which is directly proportional to the force and inversely proportional to the mass of the object. Right. That's Newton's second law. As a matter of fact, I want to advise that often when the questions are being said here, what we are being asked to state is a clue of how we are going to answer some of the questions that follows. It's not an obvious case, or should we say it's not always the case, but oftenly it happens that way, right? So let's go to the next question. Draw a labeled free body diagram of all the forces acting on the 8 kg block, of all the forces acting on the 8 kg block, right? So we want to draw the free body diagram, and it must bring out we must bring out 5 forces on that free body diagram. So number 1, the object shall be represented by a dot. So try to make the dot as accommodative as possible to all the forces, as each force must be standing separately. So I have the normal force that is acting upwards. There is my normal force. Right. I also have the applied force applied at an angle. There is my applied force. It has been applied at an angle. Right. That's F there. Then I have tension acting to the left. There is my tension. Right. And then I have my kinetic frictional force acting again to the left. That's Fk there. So this is tension. Right. And then I have gravitational force acting downwards. There is gravitational force Fg. It's acting downwards. It might interest us, so this is our diagram. It might interest us also to note that the the direction of our arrow indicates the direction of the force. Number 1. Number 2, the length of the arrow that we are arrow that we are using is indicating also the magnitude of the force. So it's also important to note that, however, that is not much examinable, the magnitude being represented on the free body diagram. What is of key and paramount importance is to show the correct direction. That's what is much examinable, okay, as of now, right? So 4.3.1, let's go to 4.3.1. Calculate the normal force acting on the 8 kg block. That's the information we've been given. They want to calculate the normal force that is acting. So first things first, on the 8 kg block, indeed, we have the normal force acting upwards. But is it the only force that is acting upwards? No, it's no longer the only force. There is also the vertical component of the applied force, which we can call Fy. So there are 2 forces that are acting upwards, N and Fy. Apparently, the 2 of them should be equal to the gravitational force mg. So the 2 of them are the ones equal to Fg, right? So it means we can create an equation based on that, and that's our equation there. So we can make n the subject from there. It means n, therefore, is equal to mg, since gravitational force is equal to mg, minus Fy, the vertical component of the applied force. Okay, so we can therefore calculate m, the mass is 8, multiplied by 9.8, the gravitational acceleration, minus Fy. Fy, we have been given an angle to the horizontal, so Fy is given by F sine theta, if that is the case from the trig ratios. We may just know that as well, it saves us in the exam. Okay, so that's 60 sine 20. Okay, and what do we get? 57.88 Newton. Right, that marks our normal force. Then the next question is now saying determine the kinetic friction force acting on the 8 kg block. So we want the kinetic friction of the 8 kg block. The kinetic friction Fk is equal to mu k n, because it depends on two factors. Mu k, the coefficient of kinetic friction, which represents the type or the texture of the surface, and then the normal force. These are the two variables that the kinetic frictional force depends on. So we have been given mu k as 0.2 multiplied by the normal force, which is 57.88, and that gives us 11.576. Right, and that becomes 11.58 Newton, 11.58 Newton to two decimal places. Right, so that's our kinetic friction there. Then the next question is now saying, determine the magnitude of the tension in the string. Calculate the magnitude of the tension in the string. Right. I'm going to clear off my screen then. Right. How can we calculate it? Right. We can start with the 4 kg, with the 8 kg block. So we can say for the 8 kg block, right, F net is equal to MA. What are we doing now? We are considering the forces acting in the horizontal dimension where the tension is acting. Right, so F net is equal to MA. You were told there was an acceleration that occurred to the right there. Right, so which forces specifically for the 8 kg block were acting? There is the horizontal component of the applied force Fx, and it's acting to the right from the tail going towards the head of the applied force. It means Fx is acting to the right, while Fy, we said it is acting upwards there. Right, so we said we have Fx, right, but then the tension is acting to the left. We witnessed it on the free body diagram, and that's one major reason why we need a free body diagram to enable us to see the direction of the forces that are acting. So taking right as positive in this circumstance, it means Fx minus T minus Fk is equal to Ma. These are the forces that are acting to the left tension and Fk. Right, and also our acceleration is to the right, because we were told that the acceleration is going to the right. Right, so we can therefore substitute the value 60 cos 20, that's Fx there for us, minus T, the unknown tension, minus Fk, which we have calculated already, 11.58, is equal to 8, the mass multiplied by A, the unknown acceleration. Right, so by so doing, we have created an equation. We can simplify it: 60 cos 20 minus 11.58, and that can give us 44.802 minus T is equal to 8A. That's an equation which has been formed, but it is having two unknown values, tension and acceleration. Now, here is the good thing. The acceleration of the 8 kg block apparently happens also to be the acceleration of the 2 kg block, because the two are interconnected. It means if the 8 kg block moves, the 2 kg block shall also move with the same acceleration. Point number one. Point number two, this string that connects the two, there is tension. On the 8 kg block, the tension is acting to the left, because tension always acts away from an object. But on the 2 kg block, it will be acting upwards. However, that tension is equal for the 8 kg block and for the 2 kg block. Hence, using that knowledge, there are now two things that these two blocks are sharing in common. It is tension and acceleration. Hence, we can form simultaneous equations based on that. So we then go to the 8 kg block and we say we go to the 2 kg block and we say for the 2 kg block, we are now creating also equation based on the 2 kg block. I take upwards as positive because the 2 kg block will be moving upwards if the 8 kg is moving to the right. The 2 kg will move upwards. So we'll say again, F net is equal to MA. F net is equals to MA. So it means which forces are acting on the 2 kg block. Apparently, there is tension acting upwards on the 2 kg block. There is tension, it's acting upwards, and that's tension there for us. And then there is a gravitational force for the 2 kg block. It's acting downwards. T there. So we can say T minus 2 times 9,8. We are talking of the 2 kg block is equals to 2 times A, which is 2A. Right, so simplifying that, it means we have T minus 19.6 is equals to 2A. Two equations have been formed. Equation 1 that was formed from the 8 kg block, and equation 2 formed from the 2 kg block, which means these two equations can now be solved as simultaneous equations, right? How can we solve them? Right, we can first come to this first equation and make T the subject. It means it's going to be 44.802, that's 8 there, 02 minus 8A is equal to T, right? We've transposed our negative T to the right and taken a negative 8A to the left, right? We can do also the same again for the equation 2. We will say T is equal to 19.6 plus 2A, or 2A plus 19.6, right? So it means T is equal to this. At the same time, T is also equal to this. It means these two equations, these two, 44.802 minus 8A should be equal to 19.6 plus 2A. So we formulate an equation based on that. So what are we going to do? We will simply say 44.802 minus 8A is equal to 19.6 plus 2A. It might interest us to see, but I didn't round off here. I'm avoiding rounding off my figures too soon before the final answer. So I've equated the two equations, and I'm now solving for A, the acceleration. So I take variables to one side, I take constants to the other side in solving my equation. So it means I can say 44,802 minus 19.6 is equal to 8A plus 2A. Right, I hope we are moving along together there. I'm trying to show as much working as possible. So if we subtract these two, we have 25.202 is equal to 10A. Right, so we can now divide by 10. We can divide by 10 to find our A. So divide that by A. We have A, B, we divide by 10, sorry, divide by 10, divide by 10. Right, so what are we going to get? A is equal to 2.5202, which is 2.52 meters per square second. Mind you, we are looking for A, so we divided by 10 there, both sides. So divide by 10 here, divide by 10 there. Right, so A is 2.52. Right, having identified, or we can just use 2.502 again. So tension, therefore, is equal to 2 multiplied by 2,52 plus 19.6 is the one that I'm opting. I'm just taking now, substituting into any one of these. Remember, T is equal to this, and at the same time, T is also equal. So you can now substitute into any one of them to determine T. So I've substituted into one of them, which gave me 24.66404, which is 24.64 Newton to two decimal places. That marks our tension T. Right, so we have answered this question. Let's go to the other question. Right, question 4.4 is now saying a 60 Newton force is now applied at an angle of 48 degrees which means the angle was 20 there. Now they are saying the angle is 2048 to the horizontal. How will this change affect the kinetic friction experienced by the 8 kg block? Choose from increase, decrease, or remain the same, and give a reason for the answer. Right. Apparently, the kinetic friction will increase. Will decrease. Why? Because an increase in sine theta results in an increase in the vertical component of the applied force. And since N is equal to mg minus f sine theta, it means N decreases, thereby decreasing Fk, since Fk varies directly with N. Right. I just want to explain further on what we are seeing. Number one, we have agreed that Fk is equal to mu Kn. Already calculations have been done, which means Fk and the normal force, they vary directly. When one increases, the other one increases. When one decreases, the other one decreases. So all we want to do to see what will happen to Fk is to monitor what will happen to N. N is being given by mg minus f sine theta, right? So what has happened to f sine theta if our angle increases to 48? We can just punch that to say 60 multiplied by sine sine 48. Even without punching, it's good to note that if this angle increases to 48, the vertical component of our applied force, Fy, will increase. And when Fy increases, which means this value here will increase. And when it increases, it means we are now subtracting a bigger value than the one we were having from mg, our gravitational force. So we are now subtracting a bigger value, which means by so doing, that will cause a decrease in the normal force, because the normal force is dependent on both of them. So if this value increases, it means normal force will decrease. And when normal force decreases, apparently Fk will also decrease. So that's why we are saying it decreases. Fk decreases. And we are saying this is due, our explanation now giving a reason. We are saying an increase in sine theta results in an increase in the vertical component of the applied force, right? And since N is equals to mg minus f sine theta, N decreases, thereby decreasing Fk, right? That's the explanation we are giving. Right, let's quickly go to the next question. Right, our next question is question number 5. Right, question number 5 is saying the diagram below shows a satellite of mass 3,500 kg at a distance of 2,600 meters above the surface of the Earth. State the Newton's universal gravitational law in words, right? So in just stating it directly, it states each body in the universe attracts every other body with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. That's question 5.1 for us there. 5.2, explain the difference between mass and weight, right? Mass is the amount of matter of an object, while weight is the measure of the gravitational force on an object. That's weight, in short. There are differences, okay? 5.3 is now saying, calculate the force that the Earth exerts on the rock, right? So use m1 over r squared. That's our universal gravitational law. Okay, so substituting G, it's 6.67, right, times 10 to the power of negative 11, right, multiplied by, what is the mass of the rock, of this, the mass of the, shows it's the mass of the rock. It was supposed to be the satellite there, right? So we are saying that 3,000 what? 500. Apparently that's an error there. So that's 3,500 times the mass of the planet Earth. So the mass of the planet is given on table 1 on the data sheet. We'll be having it, that's 5.98 times 10 to the power of 24 kgs. Right, remember mass must be in kg. Same applies. This one is also given 6.67 times 10 to the power of negative 3. Right, that's 6.67 there times 10 to the power of, right, divided by. Now we have the distance 2,600 to the surface of the planet Earth. However, it must be to the center of the Earth, because there we are saying, according to the universal law of gravitation, it is the square of the distance between the centers. So we need to add the radius of the Earth, which is 6.38 times 10 to the power of 5. It's given again on the data sheet, bracket squared, right? So that gives us 3.40 times 10 to the power of negative 18 Newton. Right, that's our force. We've performed the calculation there. Let's go to the next question, which is 5.4. Right, the same rock is now brought on the surface of the Earth. Right, will the force between the Earth and the rock increases or decrease, increase, decrease, or remain the same compared to the force calculated in 6.3, fully explained without any calculation? Number one, it increases because the distance has been decreased and the r squared has decreased. Therefore, Fg varies inversely with the distance, so it decreases. Right, that's 5.4 there. Let's go to question number 6. Right, and question number 6, the question is saying a charged sphere R and S, the charged sphere R and S are placed in a vacuum at a distance 20 centimeters apart. Define Coulomb law. So that's the first question we are having there. It says the magnitude of the electrostatic force exerted by one point charge on another is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. That's Coulomb's law there, and basically it is just it has been derived from the universal gravitational law, Newton's universal gravitational law, right? So basically it's one and the same thing there, right? So let's go to 6.2. The question is saying, calculate the electrostatic force sphere R experiences due to sphere, calculate the electrostatic force sphere R experiences due to the charge on sphere S. That's our 6.2, right? So in calculating that, we are using that Coulomb's law. As a matter of fact, I would want to continuously emphasize on the fact that the main reason why often you are given this, it serves often as a clue on what to do to the questions that are following. So it means here we can use Coulomb's law, which is saying Fe, the electrostatic force, is equal to K Q1 Q2 over R squared. Right. So we can therefore just substitute the information that we have. K, that's 9 times 10 to the power of 9 is given among the constants on table 1 on the data sheet. Multiplied by, right, we have a charge there of 3 times 10 to the power of micro is 10 to the power of negative 6. Multiplied by 3 times 10 to the power of, again, negative 6. divided by 20 centimeters, right? So that's 20 times 10 to the power of negative 2, right, bracket squared. There we are. So that's 2 comma 025, which is the same as 2 comma 03 to 2 decimal places Newton. That's the electrostatic force. But we have been told only to calculate the electrostatic force. It means we want the magnitude and the direction. They are saying the electrostatic force sphere R experience is due to the charge on S. So it's R that is experiencing the electrostatic force. So in which direction shall R go? Shall R be repelled away from S, going to the left, or it shall be attracted towards S? So we are checking now the charges. This is positive, this is negative. So it means, therefore, R will be attracted towards S, so it will be to the right. So this is 2.03 Newton to the right. Okay, that's 6.2 there. Let's go to 6.3. If sphere S is now removed, is now replaced at a fixed position, and the sphere R freely moves towards S, will the acceleration experienced um, by a sphere R towards S, towards sphere S be increasing, decreasing, or constant? It will be actually increasing, right? Explain the answer, that's 6.3.2. Explain the answer to 6.3.1 by referring only to the forces. So it is because as distance decreases, the force between the two tend to increase, because we know that acceleration varies directly with the force. So we are saying as distance decreases, the force between the two tend to increase. That's 6.3.2. Let's go to 6.4. A third sphere T with a charge of negative 2 microcoulomb is placed at right angles to the sphere S at a distance of 15 centimeters from sphere S as shown below. Right. First question, draw the vector diagram showing all the forces acting on sphere R due to sphere S and T, including the net force. Right. We can draw it in this way, right? Starting with the force on R due to S, it would to the right, as we have indicated there on the question we've just done, FSR, right? It will be to the right. Then, what about the force that R will experience due to T? T is a positive charge just like R. So R cannot move towards T, because if it moves towards T, it means it's being attracted towards T, which is not correct. It has to move away from T, which means it is going down, because it's in the vertical dimension. Remember, this is the vertical plane, so it can either move upwards or downwards. This is the horizontal plane. It means R was supposed to move either to the left or to the right, so we said it moved to the right. So in the vertical plane, it will move downwards. Then it goes down. We indicate also that's F T R there. That's F T R. Right. So we now join from the tail towards the head. There we are. That becomes F, the vector diagram. Right. Or we could have drawn it also like this, starting first with the vertical FTR. So we can draw it as this. Right, there it goes. Then at the head of T, we now draw. Do it kindly take note. Each force is being drawn from the head of the other. Right. Then we now join from the tail towards. I want you to also take note that F is still facing the same direction that it is facing here. So it is still in the same direction. Right. Alternatively, we could have drawn like this, knowing that FSR is going in this direction. There is our FSR. Then on the same position, we also draw FTR going downwards, as we have seen there that FTR is acting downwards. So we have FTR there, it's acting downwards. We can call it this one FX, we can call this one FY, we can call FX, FY, will still be correct. Then right at the center here is now where we draw F, as if we are forming a rectangle, and we just focus on the diagonal of the rectangle, which means the diagonal becomes our F. That's basically what is happening there. But do not show that rectangle, you just show only what I have just shown there, just like that. There we are. Here do not show anything else other than what we are having there. I saw that's F that we have shown in the center there. That's our F. It's one way of doing it. Let's go to the next question. It's now saying calculate the magnitude of the net electrostatic force on sphere R due to S and sphere T. Right. So already we have the force on R due to S. We did calculate it. Right, we shall need it. It is now marking our F or Fx or FSR. Right, so what we now want is FTR. That's what we want to calculate, or we can now call it F by K QT over R squared. Right, so just substituting the values that we have, 9 times 10 to the power of 9 multiplied by 2 times 10 to the power of negative 6. Remember, that's the charge at T, right? And multiply by QR, which is 3 times 10 to the power of negative 6, right? Divided by the distance between them, and that's apparently 15 times 10 to the power of negative 2, bracket what, squared. Newton net is equal to the square root of FTR squared, right, using Pythagoras. So that's what we do for point charges in 2 dimensions, right? So that's the square root of 2,4 squared plus 2,03 that we had calculated the other time squared, and that gives us 3.14 Newton, right? That's our force there, F net. We have calculated it, right? So that's F net for us. Let's go to question number 7. So there is question number 7, right? So question number 7 is saying X is a variable point in the electric field of a charged sphere Y, and R is a distance between point X and center of sphere Y as shown below. Right. Learners determine the magnitude of the electric field E at point X for different values of R. Sphere Y is then replaced by another sphere Z of different charges, and another set of results are obtained for different values of R. The graphs below are obtained from the results for sphere Y and sphere Z. EA is the magnitude of the electric field at a distance of 0.05 meters from the center of the sphere Y. Right, use the graph to answer the following questions. 7.1, state the relationship between the magnitude of the electric field E at a point and 1 over R squared, meaning the inverse of R squared. Right, so apparently these two vary directly, so it's directly proportional to 1 over R squared. It's directly proportional. As a matter of fact, it's inversely proportional to R squared. But when it comes now to 1 over R squared, they vary directly. They are directly proportional. Right, so that's 7.1 for us. 7.2 is now saying calculate EA if the numerical value of the gradient is of the graph for sphere Y is 740, right? So what we can just do is we take a point, right? Since the numerical value of the gradient is 740, we can simply say 740. We imitate the calculation that we can have for our gradient. So we say this point here, we have coordinates 1 over 0, 0.05 squared s to EA. And then we have another point here, 0 s to 0 at the origin here. We have another point 0 s to 0. So we are using these 2 points to calculate the gradient. So we'll say EA minus 0 over 1 over 0, 0.05 squared minus 0, right? Cross multiplying there, it means EA is equal to 296,000 Newton per coulomb, right? It's just a cross multiplication. Then we have to just multiply 1 over 0, 0.5 squared both sides. So we end up having EN being equivalent to that. All right. Let's go to the next question. The next question is saying 7.3. How does the magnitude of the charge on a sphere Z compare to the magnitude of the charge on a sphere Y? Choose from greater than, smaller than, or equal to. Give a reason for your answer. So apparently it is greater than, because gradient is proportional to Q, Q the charge, and graph of sphere Z has a steeper gradient than graph of sphere Y. So we are simply comparing the steepness of the two graphs, and we are witnessing that the graph of Z has a steeper gradient than graph of Y. Without even performing the calculation, the steeper the graph, the greater the gradient. And apparently the gradient is representing Q, the charge. So this marks the last question in our revision, and the grand total there we are seeing is 100, and this marks the end of our revision. I would just want to kindly ask us, for those who haven't subscribed, to just subscribe to our channel. Okay, I thank you.